Okay, so welcome back. And our next class of lipids is going to be something called terpenes. Turpenes. Terpenes. And terpenes are quite a large family of lipids. These are classified as a lipid, of course, because we're talking about the lipid lecture. And we've got about 20,000 terpenes that are fairly known. And most of them come from natural sources. That's where we find a lot of these. And the natural sources are really within the flowers that we like to pick and smell. So on Valentine's Day, when you smell that nice rose, think about the terpenes that could be involved in that rose or in that geranium or maybe in that peppermint plant. Maybe you're one of those people that don't like roses but like herbs instead. Who knows? They're out there. But these are what we call terpenes, and they're a very diverse class of lipids. Again, there's more than 20,000 terpenes, and many of them are found in what we call the essential oils, or they're extracted from plants that smell very, very good. They can be hydrocarbons. So hydrocarbons, of course, are anything made up of largely of carbon and hydrogen. And this is a very common terpene structure. Or they could have other things involved in them as well. And something like that would be oxygen. So it's not uncommon to find oxygen or alcohol containing groups with these terpene structures that we will see. If they do have oxygen, we have a special term for that. We changed the name of the terpene and we call it a terpenoid instead. So this is just a special name that's given to a terpene that has an oxygen in the structure somewhere. Now, certain terpenes and terpenoids, of course, because they smell good, they've been very commonly used in spices, in perfumes, and medicines for thousands of years. So this is a structure that's been around for quite some time. The family is quite large. They do smell good, very similar to an ester. A lot of the esters smell good as well, right? Those banana oils and those pineapples and the cherries and the almonds, a lot of those were ester-based compounds. So things like this would be peppermint oil, known as menthol, geranium oil, ginger oil, celery oil, you name it. Any of these essential oils are typically terpenes as far as the chemical structure goes. Now, after all of these years, when we take a look at terpenes, we see something very common with them. So what is really the thread that binds them together? Well, it seems that they have carbons in multiples of 5. So 5 carbon, 10 carbon, 15 carbon, 20 carbon, 25 carbon. That's the way that they typically come. Now, what's the rhyme and the reason? Well, we don't quite understand it fully, but we can give you an insight of why these 5 carbons are coming around the way that they are. So they do show up in 5 carbon chains, multiples of 5 at least, and that's the thread or the bonding that holds all of these terpenes together as a family. So the most naturally occurring compounds in the terpene family have 5 carbons, 10 carbons, 15 carbons, 20 carbons, 25 carbons, and nothing really in between those multiples of 5. There is names that we can assign these terpenes based on the number of carbons that they have. So if a terpene has 10 carbons, we call this a monoterpene. And if it has 15 carbons, we call it a sesquiterpene. If it has 20 carbons, we call it a diterpene. If it has 25 carbons, we call it a sesterpene. If it has 30 carbons, we call it a triterpene. If it has 40 carbons, we call it a tetraterpene. So the prefix that we use in the front of the terpene can give us an insight on how many carbons in total is involved in the structure. Now, is this something that I would ask on a test? And the answer is no. I would never really ask you, what is the name given to a terpene that contains 30 carbons? That's something that you'll never see. This is just kind of common background that we can introduce to get you more familiar with terpenes and why we see some of these prefixes out in front. So let's take a look at why we see these in multiples of 5. Early studies show that these terpenes are made up of units. And these units are called isoprene units. So this is where we get kind of the terpene from, ENE. And the ENE is also maybe symbolic to represent alkene. So alkene maybe involves a double bond, and there could be a structure here in isoprene that has a double bond. So what is this isoprene unit and what does it look like? Well, the isoprene unit kind of starts off with a 4-carbon chain, and there is a double bond here, and there is a double bond here, and there is a methyl group that kind of points up here. And this is the structure that we call isoprene. And these isoprene units begin to come together, begin to link together, and this is what makes the terpene molecules that we will see in a couple of other slides. So we have a head associated with the isoprene, and we have a tail that's associated with the isoprene. And if I take a look at the isoprene unit, the head is here up at the top. Here's the head, and the head is the carbon, and a methyl attachment, right? So wherever this methyl attachment is at, that methyl attachment kind of gives me priority as far as numbering of the chain goes, because this is a substituent. And this substituent, we need to give the lowest number possible, and there's a carbon 1 that has a double bond here. If we number here from carbon 1, that would be the same thing. It still has a double bond. So I would prefer to number on this side just to give that substituent, because this is a tie, to give that substituent the lowest number. So because of that, this carbon is carbon number 1, so it's methyl group, carbon involved in the double bond, and that carbon on the end, that is the head, and this is what we call the tail of the isoprene unit. So these isoprene units begin to hook up from head to tails. So it's not uncommon to see these zigzag lines all the way through with these various methyl groups pointed off into the side out in the open, and these isoprene units begin to hook up like a train, and then this train is something that we call the terpene. So terpenes are kind of like polymers. So up here at the very top, I'm going to put parentheses. Terpenes are kind of like polymers of isoprene. Now you got to be careful because polymer means many, many units. Some of these terpenes are only made up of 2 isoprenes or 3 isoprenes. So are they really truly definition of a polymer? No, not really. But it's something that we can use to maybe think about and remember what a terpene is made up of. So this is what we call the isoprene rule. The isoprene units are linked together in a head-to-tail fashion, and they form terpenes, and this is what we call the isoprene rule. Not only can these basically line up to give us chains, right? We can also get cyclic structures that come from these isoprene hookups. So isoprene can hook together in a straight chain, or isoprenes can also hook up to form our ring structures for us. So either one of these are okay to describe and to kind of end up with. And these ring structures are actually very common within the terpene family. So for instance, let's take a look at 2 isoprene units down here below. We do have a 4-carbon chain, double bond, methyl, and then we have another 4-carbon chain, double bond, and methyl. And what we will see happen is that 2 isoprene units can actually hook up, and they can give us something that looks like this. So here's the double bond. It's been broken, and then 1, 2, 3, and 4 carbons, 1, 2, 3, and 4 carbons. So this is kind of the dividing line here. And this starts the new isoprene unit, and then this thing can venture on and on and on and on and on. So this again could be a polymer if it wants to be a polymer, but that's the story of how isoprenes begin to hook up. So I'm going to put dot, dot, dot here in front because that repeats, and this could be dot, dot, dot afterward because that could repeat on and on and on and on as well. Not only that, but they can also form rings for us, so we can have terpenes that have oxygen in them, right? We saw that, so let's put an oxygen here. So there's a terpene, right? Here's a double bond, carbon double bond, and then we see a methyl group, so this would be the head of the terpene, and then we see a carbon and a double bond O and another carbon there. And then down here below, let's just draw another terpene that looks something like this. So that could be a terpene as well. Carbon, carbon, double bond. There's a methyl group that's hanging off. So because of that, this is labeled as an isoprene. And we can actually get these two things to start forming a ring with each other. And that's how they do it. They utilize those double bonds in those structures, and there we go. There is a ring. Now, I've erased that double bond because it got a little ugly. But let me put it back on there and draw this six-membered ring a little bit better. But there's a terpene that has formed a ring now, and this terpene is called carvone, and carvone is very commonly extracted from spearmint oil or a component of spearmint oil. We have carvone in our laboratory if you want to take a smell of it, and you will see that it smells just like spearmint. So next time you chew that spearmint gum, think of the carvone, which is the terpene that you're chomping on. Not only that, but you take a look at some of these isoprene units, and these isoprene units, if they begin to link up fashion to fashion to fashion, we get in this thing called tetraterpene, and this tetraterpene goes by another name, and this other name that these are known by are called carotenoids. So whenever we talk about carotenoids in the laboratory environment, we are talking about terpenes, which are lipids. And these carotenoids are very important because you've worked with the carotenoid already. And that was at the beginning of the instrumentation course when you handmade your column, chromatography column, and you put tomato paste extract in it. And you were trying to separate the lycopene from the beta carotene. That is a carotenoid. If you go back and take a look at the definition in the background of that laboratory, it walks you through the whole carotenoid description and how it basically tells you that beta carotene and lycopene is classified as a carotenoid. If you take a look at the number of carbons that make it up, you're going to see 40 carbons that are there. So carotenoids are tetraterpenes, and lycopene, the compound responsible for that red color in the tomatoes and your watermelon, and beta carotene, the compound that causes carrots and apricots to be orange, those are examples of your carotenoids. So we've talked about some of these physical properties and chemical properties before. Go back and remember that lab. What kind of solvent did you use to extract those compounds? What kind of solvent did you use to push those compounds through the column? You've worked with them before. You should know a little bit about them. Not only that, but you saw really a system in place with those compounds that had conjugated double bonds all the way down the line. So double single, double single, double single, double single, and then you saw these methyl groups point up and down along the course of the way. So because of that conjugated system, these things became colored. And of course, it was this color that you were looking for in the column when you did column chromatography. You were looking for those reds and those oranges, and you were separating things based on those color bands that were coming through that column at that time. So there's the story for carotenoids, a little bit of terpene background, and what makes a terpene up. We now know that those are called isoprenes, and we can take a look at the number of isoprenes. My suggestion is if a question wants to know how many isoprenes make this thing up, take a look at these methyl groups and use the methyl groups as an indicator. So here's one methyl group, that probably is one isoprene unit. Here's two methyl groups, and there's my second isoprene indicator. So use that as a rule of judgment. In the next video, we'll continue on terpenes.